I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die.
Welcome to the 33rd season of the Mount Tamalpais Astronomy program, co-presented by the Friends of Mount Tam and by Wonderfest, the San Francisco Bay Area beacon of science. My name is Tucker Hyatt. I'm founding director of Wonderfest, and I'm honored to represent Tinka Ross, illustrious founder of the Mount Tam Astronomy program. All right, tonight's speaker comes to us from the East Coast, where he's stayed up extra late, and just in our honor. He is Eliot Quataert, professor of astronomy and professor of astrophysical science at Princeton University. Eliot earned his BA in physics from MIT and his PhD in astronomy from Harvard. Today, his research spans a wide range of challenges, from the astrophysics of stars and black holes to the formation of galaxies. Dr. Quataert's many awards include the Bart Bok Prize from Harvard and the Helen Warner Prize from the American Astronomical Society. In 2012, Eliot was among only 21 theoreticians in physics, computer science, and mathematics to be granted the all too modest title of Simons Investigator by the Simons Foundation in New York. Recently, Eliot was elected to both the American Academy of Arts and Sciences and to the National Academy of Sciences. Best of all for us tonight, I'm still admitting folks, Professor Quataert enjoys and is terrific at teaching and public outreach. In 2010, he won the Noyce Prize for Excellence in Undergrad Teaching at Cal. Go Bears. Please welcome Professor Eliot Quataert.
Thanks, Tucker, and thank you all for joining tonight. It's very nice to be here. I was at Berkeley as a faculty member for many years and gave, as I recall, 2 of the Mount Tam lectures in person, and those were honestly among my favorite talks I've ever given, both the engagement of the audience and the amazing location. So this won't quite live up to it in terms of location, but hopefully you'll be engaged and excited about the science that I'll tell you about. So I'm basically going to tell you over the course of this talk how it is that astronomers took this remarkable image that many of you have probably seen, the Event Horizon Telescope of the environment close to the event horizon of the black hole in a relatively nearby galaxy, M87. I should say from the start that I'm not a member of the Event Horizon Telescope team. I'm a theoretical astrophysicist. I do modeling of a variety of different types of phenomena, and some of what I do is actually models both predictions and then more recently interpretation of the kinds of observations that the Event Horizon Telescope makes. And it's really been just an extraordinarily exciting time to see these results as they've come out and have continued to come out, with the most recent results actually just coming out about a month ago or so. So the subject of today's talk is going to be the science of black holes and the real astrophysics of black holes. But this is a subject that really imbues popular culture. Everything from graphic novels to Disney movies to perhaps the most recent incarnation of the black hole fixation in Hollywood was the Interstellar movie about 7 years ago now. For those who don't know this, the original script for Interstellar was written by Kip Thorne. Kip Thorne is an astrophysicist at Caltech who won the Nobel Prize in Physics actually for the development of the LIGO gravitational wave observatory. And in his later years, he has moved into script writing and a variety of forms of science communication through movies and television. My favorite indication of just how much black holes have made it from the realm of science to the realm of popular culture is that if you go on Amazon and you search for black holes, when I did this search a couple of years ago, I got 101,844 hits. Quite a few of the first ones are actually things that you might know. Probably many of you don't know the first one. This is actually this graphic novel that's shown here, another version of that. The Disney movie, The Black Hole, a book by Neil Tyson on death by black hole. In addition to the more familiar ways that black holes show up on Amazon, you can also find them in health and personal care, which mostly has to do with weight loss and liposuction and things like that. So I could go on, of course, for the whole talk, talking about the intersection of science and science fiction when it comes to black holes. But what I want to do now is really turn and tell you about the science that's at the heart of this story. So I'll start by telling you a little bit about what black holes are, how we think about them as physicists and astronomers. And then I'll tell you about how we actually find them observationally, how we model them and interpret them theoretically. And that part will really be entirely centered on the Event Horizon Telescope observations of M87 and what we've learned from them, and really what information is encoded in this remarkable image. So the story about black holes is really a story about gravity. And so I want to tell you a little bit about what black holes are, what physics we think describes them. But it's useful to start actually with something a little bit simpler. In this case, stars, planets, objects like that. Gravity is a relentless force in the universe. It acts on everything. It acts on all forms of mass or energy. In the case of an object like a star or a planet, gravity is this sort of relentless inward pull due to the combined action of all of the mass that makes up the object. And that's what's shown in the kind of blue arrows here, is the inward pull of gravity caused by all of the mass that makes up the sun, say, in the image of the sun here. And what stops the sun from collapsing in on itself due to the inward pull of gravity is that the sun is very hot, temperatures of tens of millions of degrees at its center. The heat is generated by nuclear fusion at the center of the sun. And the fact that the interior of the sun is so hot compared to the surface creates an outward push due to the high pressure of the interior of the sun. And that outward push due to the high pressure basically almost exactly balances the inward gravitational pull and means that the sun is in this sort of happy state with gravity being balanced by pressure pushing out. The Earth is in a very similar state. The interior pressure is pushing out, maintaining the kind of shape of the Earth against the gravitational pull of the matter that makes up the Earth. In the case of the sun has been in this kind of current state for about 4.5 billion years. It'll be in that state for another 4.5 billion years. And then eventually the sun will run out of nuclear fuel and it will end up as what we call a white dwarf, an object supported by a different kind of pressure. But stars much more massive than the sun can't become white dwarfs. They actually end their lives collapsing to form black holes. And I'll talk about that a little bit more as we go. The balance between pressure and gravity on the Earth or the sun is not absolute. Objects can escape the gravitational pull of both the Earth and the sun. In the case of the sun has a wind where it ejects matter out into space. In the case of the Earth, we're able to successfully launch rockets that can escape the gravitational clutches of the Earth. And in physics, we describe how hard it is to escape the gravitational clutches of an object in terms of what's called the escape speed of the object. That basically depends on how strong gravity is. The escape speed depends on the mass and the size of the object. More stuff, larger mass, gravity is stronger. Gravity is harder to overcome. The escape speed is larger, meaning you would need to throw something at a higher speed to actually escape the surface and not come crashing back down. Likewise, gravity is stronger when objects are closer together. So if you have a planet or a star that has a smaller size, a smaller radius, its gravity is stronger. It has a higher escape speed. And again, its gravity is harder to overcome. You need a higher speed to escape the gravitational clutches of that object. In the solar system, the sun's escape speed is about 1,000,000 miles an hour, which is almost 60 times larger than the escape speed of the Earth, which is about 27,000 miles an hour, 11 kilometers a second. So that's how fast you would need to throw a baseball, for instance, if you actually wanted that baseball to escape the gravitational clutches of the Earth. With a rocket, it's not sort of a single thrust, right? We have engines that are constantly burning fuel, but it's the same basic idea. You effectively need to give the rocket enough of a push through its engine that it achieves this speed of 27,000 miles an hour and is able to escape the gravitational clutches of the Earth. And that's effectively what was done, for instance, when Voyager left the Earth and left the solar system. In the late 1700s, two pioneering physicists and mathematicians, Michel, who was really a geologist, and Laplace, who's a very famous mathematician, they combined two ideas of Newton's theories of nature. One of those was this idea that I just explained to you about gravity and escape speed. And the other was the realization that even light, which travels at the fastest speed we know of that anything can travel at, even light has a finite speed. It's an enormously fast speed. It's about 1 billion miles an hour. If I were giving this lecture on Mount Tam, I would use my laser pointer and bounce it off of something and tell you that it would take light a certain amount of time, something like 10 billionths of a second, to go from the laser pointer to reflect off of the screen and to go to your eye. So light travels at an enormously fast speed, but it still travels at a finite speed. And what Michel and Laplace asked is this incredibly brilliant, ingenious question. And often doing science is about asking the right question. And they definitely asked the right question. The question they asked was, what if a star were so small that its escape speed was larger than the speed of light? Namely, take an object and make its radius smaller and smaller and smaller. That makes gravity stronger and stronger and stronger. And eventually that object would have an escape speed larger than the speed of light. And that would be a star that we couldn't see. A star that, at least by this Newtonian reasoning, could emit light from its surface, but that light could not reach a distant observer, because nothing traveling even at the speed of light could escape the gravitational clutches of that object. And Michel and Laplace even calculated how large the object would have to be. They combined measurements of the speed of light with Newton's result for the escape speed of an object, and they calculated that if you took the Earth and you shrunk the Earth down to about the size of a marble, about 1 inch in diameter, inch in radius actually, then you would have an object whose gravity was so strong that not even light could escape. Or because gravity depends on both mass and radius, if you took the sun, which has a much larger mass than the Earth, and shrunk it down to about the size of a city, then the sun would become a star whose gravity was so strong that light couldn't escape. And this is really still the key basic idea behind black holes as we understand them today. Our understanding is much more sophisticated. It's much more mathematically sophisticated. It's conceptually more involved in many ways. But the core idea is correctly captured by Michel and Laplace's kind of reasoning that I've given you here. Somebody's asking in the chat, if you were inside a black hole, could you see the light because it wouldn't have to travel as far? And that's correct, that if you were close to the surface of the black hole, the event horizon, or inside of it, you could still see the light. This is really a statement about the fact that the light can't get very far away, not that somebody close to the center of the black hole or close to the event horizon couldn't see things around them. Okay, so this idea about black holes sort of languished, to be honest. It languished for a while, for well over 100 years. And it languished basically because Michel and Laplace cheated. They combined Newtonian ideas of gravity with ideas of light, when in fact Newton's theory of gravity doesn't really apply to light. It doesn't apply to light because Newton's theory of gravity doesn't apply to objects that move as fast as the speed of light. And Newton's theory of gravity also doesn't apply to objects like light that have energy but don't have what's called rest mass, the mass an object has if it's not moving. And that's because light actually can't ever stop moving. And it wasn't until Einstein's theory of relativity was developed in the early 1900s that we developed a more complete understanding of what black holes are. And as I already said, the core idea about black holes in Einstein's theory is still very much the same. There's a wrinkle to it, which is that in Einstein's theory, if an object is small enough, and really that means smaller in size than the event horizon that Michel and Laplace calculated, then gravity wins over everything. It wins over any possible pressure in the universe. So the pressure that's holding gravity at bay in the Earth or the sun or a white dwarf or Jupiter or a neutron star. If you make an object small enough, gravity wins out over all of those forms of pressure. The object collapses down to the very center, and it collapses in on itself to a point at which gravity wins out and nothing, not even light, can escape the gravitational clutches of the object. And so that's sort of shown schematically here. The event horizon is the point of no return, inside of which no information traveling at the speed of light can get out. But in fact, in Einstein's theory of relativity, all of the mass has collapsed down to the very center. And so there's actually nothing there at the event horizon. So the radius of a black hole is conceptually very different than the radius of the Earth, the radius of the sun. It's really demarcating where stuff traveling at the speed of light can get away to a distant observer if you're outside the event horizon, or can't get away to a distant observer if you're inside the event horizon. But there isn't actually any matter or stuff at the event horizon if all you have is a black hole sitting there on its own with nothing else around. This fact about black holes, that if you're inside the event horizon, you inevitably get sucked into the center because gravity wins out over everything else. This leads to what I think is really the single biggest misconception about black holes, which is that they're sort of a cosmic vacuum cleaner that sucks up everything in their surroundings, and that you have to go home tonight, meaning go from whatever room you're in right now to another room in your house or apartment, and go to sleep and worry about whether you're going to get sucked into a black hole. That's actually not the case, as the jumping knot of PowerPoint and Keynote highlights, because it's only if you're inside the event horizon that you inevitably get sucked into the center. If you're far away from a black hole, Newton basically got the theory of gravity right. And in the solar system, we don't get sucked into the sun. The gravity of the sun causes the Earth to orbit around the sun, but not to inevitably fall into the sun. And the same thing is basically true in Einstein's theory of general relativity, that if a black hole replaced the sun, nothing about the orbits of the planets or the asteroids or the moons would change. They would continue to orbit the way they do. Obviously, nuclear fusion doesn't operate in a black hole the way it does in the sun. And so the solar system would get very cold and things would die, and so that would be bad. But from the point of view of gravity, actually not much would change if you replace the sun with a black hole. Okay, so that's sort of the 20-minute introduction to the physics and astronomy of black holes. And now I want to turn to more of the observational question of how do you actually find them? How do you find black holes in nature? How can we study them? How can we characterize their properties? Many of you are amateur astronomers, and so you know that when you look up at the night sky and you see a dark region as shown in this image here, that doesn't mean that there's nothing there. It definitely doesn't mean that there's a black hole there. What it actually means, the reason this region is dark is because there's actually so much stuff along the line of sight between us and this region of space. There's so much gas and dust, little particles, that they absorb the light of the stars behind them. And so we don't see any of the stars that you see in the other places of this image. So finding black holes is a lot more challenging than just looking up and looking for regions where there isn't light. It's taken much more sophisticated detective work to figure out where black holes are and to measure how much they weigh and measure other properties of black holes. And there's actually multiple ways that we can detect black holes now. We can detect them through gravitational waves, through the LIGO telescope that Kip Thorne developed. But the technique I'm going to tell you about today is in some ways the most paradoxical. And it's that black holes, these objects that are defined, their very nature, their very name is given because they don't emit light. Black holes actually produce many of the brightest sources of light that we see in the night sky. And the paradox is resolved because the light is not coming from inside the event horizon, because light cannot get out from inside the event horizon. The light is actually coming from gas that's just outside the event horizon that's spiraling in, producing huge amounts of light. And that's what's shown in these two astronomical images here. The left is our good friend for this evening, the galaxy M87. The galaxy is right here where the tip of my arrow is now. And some of the gas around the black hole at the center of M87 is actually ejected in this beam that you see here that's called a jet. This is material that's moving at nearly the speed of light, like 99.9% of the speed of light. It's ejected from close to the black hole. It's ejected all the way out of the galaxy. And as this material moves away from the black hole at nearly the speed of light, it sometimes produces light that we can see as these bright regions along this linear feature. The image on the right here is another more distant galaxy, 3C273, which is very famous in astronomy circles because it is one of the first discovered and most well-studied black holes. What you're seeing here is actually that the light from the region close to the black hole at the center of the galaxy is so bright that it actually outshines all of the stars, all of the billions and trillions of stars that make up this galaxy. And only by subtracting the light that's coming from the vicinity of the black hole can we see the faint smudge of light that is the trillions of stars in that galaxy. So the process of gas falling into a black hole is what astronomers call accretion. This actually operates not just for black holes. You can have accretion onto normal stars. That's how stars form. That's how planets like the Earth form. They form in this debris of material spiraling into the newly formed sun. What's special about gas falling into a black hole is that when gas falls into a black hole, it moves at nearly the speed of light because of the strong gravity of the black hole. And that matter, as it moves at nearly the speed of light, gets extremely hot. And so it produces huge amounts of light. And the reason it gets so hot is actually something that you're familiar with from everyday experience. It's basically friction. That in this schematic diagram, this is not a real astronomical image. This is an artist's conception of what the gas spiraling into the black hole might look like. This is the conception of the jet produced that you see in this real image here of M87. Different regions of this gas are moving at different speeds. And just like when you rub your hands together, or if you were a Girl Scout or a Boy Scout and you tried to start a fire by rubbing twigs together at different speeds, the fact that you're rubbing material together at different speeds generates heat. That's what happens in this rotating disk of material around the black hole. Some materials moving at 0.9 times the speed of light, some is moving at 0.5 times the speed of light. There's friction between the different regions of the gas moving at different speeds. That generates heat, and hot gas produces a lot of light. So that's the fundamental reason why the strong gravity of the black hole, which causes things to move very fast, ends up also producing these very bright sources of light. So soon after the discovery of black holes at the centers of galaxies and the realization that they were producing these very bright sources of light, astronomers wanted to look closer and closer to the region around the event horizon of the black hole to understand what was happening as the gas really travels through this point of no return, travels through the event horizon. So how can we do that? Well, the challenge is that most black holes are pretty far away, and they're actually quite small. The size of the region where most of the light is produced in the galaxy M87 is about the size of our solar system, which is very small compared to the size of a galaxy. But that galaxy is many, many millions of light years away from us. And so what that means is that the region, sort of the size of the event horizon on the sky, subtends a very small angle. So to make it easier to see what's happening near the event horizon, what you want is you want black holes that are relatively close. That makes it easier to see what's going on, and that have large black hole masses, because if the black hole mass is larger, the size of the event horizon is larger. And it really is sort of as illustrated in this nice image here, I think. It's sort of a matter of perspective, right? The person's fingers are not actually the same size as the Eiffel Tower. They just look that way because the fingers are close to us compared to the Eiffel Tower, so they look a similar size on the sky. And it's the same idea in trying to find black holes to study what's going on at the event horizon. What you want are ones that are sort of like the pair of fingers here. Things that are close and relatively big, so you have an easier time seeing what's going on the scale of the event. It turns out that the galaxy M87 is one of the two black holes we know of that is the largest in terms of the angle that its event horizon subtends on the sky. The galaxy M87, the black hole, weighs about 6 billion times the mass of the sun, and it's about 60 million light years from us. The other black hole that's just about as good for doing this measurement, in the sense that the angle that the event horizon produces on the sky is about the same as for M87, turns out to be the black hole at the center of our own galaxy. That black hole is a lot closer. It's about 24,000 light years away instead of 50 million light years away. But that black hole is about 2,000 times smaller. It weighs about 4 million solar masses instead of 6 billion solar masses. And I'm going to focus what I tell you about today on the galaxy M87, because that's the galaxy that the Event Horizon Telescope has already observed. But for instance, this year, Reinhard Genzel and Andrea Ghez, Andrea is a faculty member at UCLA, and Genzel is a part-time faculty member at UC Berkeley. They won the Nobel Prize in Physics for studying the black hole at the center of our own galaxy and measuring very precisely the mass of the black hole. So just to give you a sense, the angle of the event horizon that M87 produces on the sky is about 1 billionth of a degree. So for comparison, this is actually the full moon rising over the East Bay Hills. The full moon subtends about a degree, about half a degree on the sky. So the angle of the event horizon of M87 is about 1 billionth of the full moon. And so seeing what's going on around the event horizon of M87 or the center of our galaxy is similar in difficulty to sitting on the Earth and trying to use a telescope to measure whether Neil Armstrong was holding up a penny, a dime, or a nickel while he was walking on the surface of the moon. So that's an extraordinarily difficult challenge. You have to measure extremely fine detail to do that measurement. So, what telescope has taken the best images of the night sky? I would argue that that's the Hubble Space Telescope. Over its iconic 30-year history, Hubble has taken just an extraordinary number of famous images. I'm showing a couple of them here. But it turns out the Hubble Space Telescope is woefully inadequate for seeing what's going on in the event horizon around a black hole. And the reason is basically because of the laws of physics. It turns out that the angle that you can measure using a given telescope depends on the wavelength of light that you're observing at and the size of the telescope. And the Hubble Space Telescope is observing with light that's similar to what our eye can see. It's a 2-meter diameter telescope. And that means it's too small by a factor of 10,000 to do the experiment we want to do. These images are extraordinary. They have an amazing amount of detail about what's going on in the universe, but they're too small in resolution by a factor of 10,000 to see what's going on near the event horizon. So it turns out the only way you can do this experiment is using a technique that's called interferometry, where you actually combine the light from multiple telescopes that are situated basically on opposite sides of the Earth. So the idea is the light comes into this telescope and you record extremely accurately everything about the light as it came in. You record exactly how bright the light was, how strong the electric field is, whether the electric field was pointing up, down, up, down, up, down as it comes to the telescope. You actually record that literally on a hard drive, okay, on a disk. Not a floppy disk, right, but a hard drive. And then there's other telescopes and you record that information, what that telescope saw on a hard drive. And then you literally FedEx or ship by airplane the hard drives to a single location. You quickly back up the data so you don't lose it. And then you combine the light from those different telescopes in a way that preserves the information, all of the details of the light as it was recorded. And it allows you to construct images that have some of the information equivalent to a telescope that has the size of the distance between the two telescopes. And that's how you cheat physics in this equation. The size of the telescope that determines the angle you can measure isn't the size of the telescope, it's the distance between the telescopes. There's a question here, can you access recordings of the light afterwards? Definitely. So the data is stored and continuously analyzed later by combining the light from multiple telescopes. This technique actually was pioneered in the Bay Area. UC Berkeley in the 70s ran a set of radio telescopes at what was called the Creek Observatory, which is in Northern California. And this is an early example of using this technique of interferometry to combine the information from different telescopes. In those days, they used a tractor to move the telescopes around to change the distance between the two telescopes and thus take astronomical images with different degrees of resolution. So to take images with finer and finer details, you would move these two telescopes further and further apart. Now what's done is that the Event Horizon Telescope actually is not really one telescope, but it's a consortium of telescopes combining multiple telescopes that are distributed across the Earth. It's a team consisting of actually now well over 200 people at more than 60 different research institutions, 20 different countries. It's a very international enterprise. The telescopes range from telescopes in Chile, Mexico, Hawaii, There's a telescope being built in Greenland for this purpose. There's a telescope in Spain for this purpose. And so it really is this sort of large international effort where one of the biggest challenges of doing this kind of observational work is you need the weather to be good at all of the different places at the same time in order to do this kind of experiment. So there's a bit of luck involved. Okay, so that's sort of a lead-in to how it is that the Event Horizon Telescope was able to take this image. And what I will do now is I'll sort of take you through and explain to you what we've learned from this picture. So first, to make sure we're all on the same page, color in this image encodes how bright the radio waves are that the telescope observed. So color here isn't connoting information like what you think color is that our eye is used to, where yellow would be something that reflects yellow light. Here, yellow, this region right here, is the region that is the brightest at the wavelength that the Event Horizon Telescope is taking this image, which is a wavelength of about 1 millimeter, or a frequency of 230 gigahertz. Orange is a bit fainter radio wave, so a less bright source of radio light. And the dark regions, the black regions, are very little radio light. So I'm a theoretical astrophysicist. So one of the things that I do is I make predictions and I interpret observations that other people make. And so because I'm a theorist, I'm going to tell you a little bit about how we understand this image by telling you about the predictions that were made before the observations were actually made. Because I think it's actually a triumph of theoretical work that was actually pioneered not by myself, but by other groups. My group did some of the work, but I would say the key work was actually done by a colleague at the University of Illinois named Charles Gammey, did a lot of the pioneering work that led to the predictions that were subsequently used to interpret the observations that I'm showing you. And this scale bar, just to give you a sense, this scale bar is 50 millionths of an arc second. An arc second is a unit of angle that astronomers use. And so the scale bar here is a little bit bigger than 1 billionth of a degree in angular scale. So again, you're looking at an image that's a patch of the sky that's like 1 billion times smaller than the size of the full moon. So really a tiny, tiny image resolved in great detail. So how were predictions made of what a black hole would look like? Well, what we did, and other groups did, is we took computer simulations of Einstein's theory of gravity, and we basically threw gas at the black hole. And we used computer simulations to tell us how gas would behave as it spiraled into a black hole. Remember, the light we're seeing here is not sort of produced by the black hole itself. It's produced by gas falling into the black hole. And so we can model that process of gas falling into the black hole using computer simulations. These are computer simulations of general relativity. And basically, in addition to general relativity, we're solving equations that are very similar to what people who predict weather do. This is called fluid dynamics or gas dynamics. The question is, wouldn't the color give details about how far the black hole is from us? Color in the sense of color in this image doesn't give us that information. But if you think of color as meaning, again, how bright is it in the radio Or is it brighter at 1 millimeter or 2 millimeters or half a millimeter? That information, which is actually the information that our eye is using, the brightness at different wavelengths when it constructs color, that type of brightness, that type of information can indeed be used to figure out the temperature of the gas and other things like that. So that analogy is good. So this shows one of the computer simulations that my group did. You're seeing sort of in time how the gas is distributed around the black hole. The black hole is the black region right there at the center. The white region is lots of gas, high density of gas. Blue is in between, green is very little gas. These computer simulations tell us where the gas is and how hot the gas is. And from that information, we can predict how much light the gas produces. And knowing how much light the gas produces everywhere around the black hole, we can follow the light as it travels away from the vicinity of the black hole, because the light that I'm talking about is produced outside the event horizon. So a lot of that light can still get away to a distant observer, and we can then use the properties of the computer simulation to tell us what this simulation would look like to a distant observer. And this is what this particular simulation would look like to a distant observer, where again, sort of yellow is bright in the radio, bright at millimeter wavelengths that the Event Horizon Telescope observes at, and dark black or dark purple is faint. So that's one simulation, okay, one prediction of what that particular simulation would look like to a distant observer. That's another simulation, different simulation viewed by an observer looking at a different vantage point, looking at the system from a different angle. That's another one. You'll notice there are details that differ, but actually there's a lot in common. There is a bright region on one side that's brighter than the other side, and there seems to be a ring or maybe two rings that are particularly bright, and then there's not much emission coming inside that bright ring and not much emission coming from outside that bright ring. One of the things we do when we do research is we look for patterns, and then we try to understand the origin of those patterns using simple explanations. And in this case, the pattern is that all these different simulations, which have different assumptions about how the gas is spiraling into the black hole, they produce similar looking images. And that suggests there's something common at play producing at least the theoretical predictions of what the gas around the black hole should look like. And so what I want to do is describe to you what those common ingredients are that produce these similar looking images from these different computer simulations. And there's basically two things I have to tell you about light around black holes to explain to you the properties of this image. The first has to do with how light is produced when objects are actually moving at nearly the speed of light. So imagine you have a light bulb that's sitting there not moving. That light bulb basically looks the same from any direction. Right? You know this from everyday experience. You take a lamp, you take off the shade, you look at it from different vantage points, and it basically looks the same. And that's because the light is going off the same in every direction. Remarkably, that's not true if the light bulb is moving at nearly the speed of light. If the light bulb is moving to the right at nearly the speed of light in this image, then an observer over here, okay, an observer that the light bulb is moving towards actually sees a much brighter source of light. than an observer over here that the light bulb is moving away from. The total amount of light produced by the light bulb is the same, but it just preferentially goes in the direction of motion of the light bulb. This is a version of what's known as the Doppler effect, which is something that you're actually familiar with in everyday experience. I think you can hear that irritating horn noise, but I'm actually not sure. That's the first time I've tried to do it over Zoom. So if not, the sound that's playing is a car horn going by and changing in pitch as the car horn goes from moving towards you to moving away from you. That's the Doppler shift. And what I'm describing to you here is similar to, though not exactly the same, as that Doppler shift that you're familiar with in everyday. Why is that relevant here? Well, we think the reason that one side of the image in this computer simulation is brighter than the other is on this side where it's bright, the gas is moving towards us at nearly the speed of light as it orbits around the black hole. Imagine the gas spiraling into the black hole as this, it's sort of like a drain in your bathtub. As the drain spirals, as the water spirals down the drain, this side is material that's moving towards us as it goes around at nearly the speed of light. It looks brighter. This side is moving away from us as it's spiraling around, and so it looks dimmer. So the difference in the two sides of brightness is because of the motion of the gas that's producing the light. Okay, second fact to understand the Event Horizon Telescope image is that gravity bends light. Gravity acts like a lens and it deflects light as light passes by any object that has a gravitational pull. The sun bends light. Human beings technically bend light, although we don't weigh enough for that to be something that's measurable. But the deflection of light by the gravity of the sun is actually one of the famous initial confirmations of Einstein's theory of relativity done by Eddington. The difference between the sun and a black hole is that the gravity of a black hole is really, really strong. And so black holes bend light in enormously strong, counterintuitive ways. And that's shown by these light rays here, where each colored path represents the path that a given light ray travels. Light that's traveling relatively far from the black hole gets bent by a mere 45 degrees, which is actually a huge amount, okay? But light that travels closer to the black hole can get bent by so much that it actually gets bent and then gets absorbed by the black hole. Or it can get bent, go all the way around the black hole once and then go flying out the other side. Or, not shown here, it can orbit around 5 times and then go flying out the other side. And that's all because of the incredibly strong gravity of the black hole dramatically changing even the motion of light itself. And we think what's going on, and we can check that this is the right explanation in computer simulations, is that in this simulation, the reason you're not seeing much light from the central patch of the image where it's dark here is because those light rays are like the one shown here, where the light that's produced by gas sort of close to the black hole a lot of that light is bent so much that the light falls into the black hole. And the reason there's this sort of ring of light is because a lot of the light that travels, around the black hole gets bent into this gets bent into this characteristic scale. There's a characteristic distance from the black hole where the light can just orbit around the black hole. And that produces the ring of light. So the deficit of light is strong gravitational lensing causing light to get absorbed by the black hole. And the ring of light is the concentration of light rays where light starts to orbit around the black hole due to the strong gravity of the black hole. And so we think the basic features of the Event Horizon Telescope image are produced by a combination then of Einstein's two most famous theories. His theory of general relativity, which produces gravitational lensing and black holes, that produces the ring and the deficit of light at the center of the EHT image. And special relativity, Einstein's theory of how things behave when they move very fast at nearly the speed of light, that produces the brighter bottom half of the image versus top half of the image, because this region is produced by gas coming towards us. This region is produced by gas going away. One difference you'll notice is that my computer simulations seem to have a lot more fine scale structure and detail than the Event Horizon Telescope image does, but that's just a property of the telescope. So to understand this, the Event Horizon Telescope team did lots of computer simulations of the kind I showed you. The results of their computer simulations are shown at the top here. And then they made mock observations of those computer simulations. And so the bottom shows what these computer simulations would look like as observed by the Event Horizon Telescope. The Event Horizon Telescope is amazing. It's taken the highest fidelity, highest resolution image of an astronomical object ever taken, but it still can't resolve all of the details that are produced by our computer simulation just because of limitations of the telescope. The telescopes can't be any further apart than on opposite sides of the Earth. And so that blurs out the images a bit to look like what you're seeing here at the bottom. So where is this going to go next? Well, I think an analogy that's useful is when Lowell first observed Mars in the late 1800s, right? He drew pictures based on images like this, where there was sort of a dark blotch and some light regions and a light region and a little dark region there, right? And Lowell actually, as we now know, horribly overinterpreted his images of Mars. He thought he saw canals, and that led to the whole notion of extraterrestrial life on Mars and Martians, and that whole kind of genre of science fiction came out of that. Today, we have remarkable fine detailed images of the surface of Mars. We know there were ancient riverbeds because water was flowing in the distant past on Mars. And this gives you a sense of how much the detail we've been able to see on Mars has changed over the course of more than a century of observations. And I think you should think of the Event Horizon Telescope image to date as a truly remarkable accomplishment, but it really is just the beginning. It is the first image in what will be a sequence of many, many, many images. And I think in the not too distant future, in most of our lifetimes, we will have movies like the computer simulation I'm showing you here on the bottom, but real movies, actual data showing how the environment around the event horizon of the black hole is changing in time as the gas orbits around and spirals through the event horizon, never to be seen again. And you may have seen about a month ago, the EHT came out with its most recent results. That was the image shown here. This is sort of the next step in the set of results that they are releasing. In this case, the image wasn't more detailed. It wasn't sort of this progression that I'm showing on the slide here, but it was actually new information that they released. It was information about the magnetic field in the gas that's falling through the event horizon of the black hole. And the lines, the sort of pointillist type lines that you're seeing in this image here, these trace out, these are providing us information about the direction of the magnetic field in the gas that's spiraling into the black hole. Okay, so I will end there. I hope I've given you a bit of a better feel for the science behind the Event Horizon Telescope, what actually produces the image that we see, and some of the remarkable technology that went into making this image possible. So thanks very much for your time. I'll be happy to answer any questions that you might have.
Boy, Professor Quataert, thank you. We will offer you great applause soon after some questions get answered. We're not letting you off the hook yet. I want to advise folks that there are at least 3 ways to demonstrate applause with Zoom here. One, of course, is just to show yourself clapping. The other is to, under reactions, to click applause. And the final method, I'm told, is to use American Sign Language symbolism for applause, which looks something like this. So save it for Professor Quataert and perhaps some others when we're finished. But we've got some good questions here. Forgive me if I don't go in order, but I'm struck here by Rajul Praek. Forgive me if I've mispronounced your name, Rajul. Could they potentially place another telescope on a satellite out in space when the first one is on Earth so they could get a more detailed image, a longer baseline interferometry?
Yes, so that's a great question. So it turns out that's actually already done. There are already small radio dishes flown, which are where the information is combined with telescopes on the Earth to create images. It hasn't been done yet at the wavelengths that this experiment is done at, which is about 1 millimeter. It's been done at longer wavelengths. There is a technical challenge. The biggest technical challenge actually turns out to be that these telescopes record a lot of data. And so you would need to transmit that data from the telescope down to the Earth. And the data rates that we can send down are actually rather slow. They are getting better and better with time. So I think this is feasible and will definitely become feasible, more and more feasible in the coming few years. So I think there's several different ideas. One is that actually you could just have a few satellites orbiting around the Earth and combine the information from those satellites, or you could also then try to combine that with telescopes on the ground as well to create higher resolution images. So this is definitely a direction that a lot of people are thinking to try to get, first of all, to avoid the weather problems that astronomers always have, but also to get larger distance between telescopes and hence get higher resolution images. So great question.
Yeah, thank you, Rahul. Greg J. has his virtual hand raised. Greg, please unmute yourself and fire away.
Oh, thank you. I had 2 questions, actually. The first is in the diagram you showed us of the light rays coming in at different distances from the black hole, such that some of them can orbit. Is there interesting information or interesting phenomena that come from I guess, the big change in path length between rays at different diameters?
So there is interesting, so part of the reason, a large part of the reason that you get this sort of ring-like feature in the emission is precisely because those light rays have traveled a longer set of path lengths. So more gas has contributed to the emission along that set of path lengths. And that's actually that's a significant part of what makes this brighter, is that path length effect. The other effect is that there are certain properties of the light specifically related to the direction of the electric field that makes up the light, the direction that the electric field is pointing. There are certain properties of that electric field direction that depend on how much gas the light has traveled to on its way from where it was produced to us. And so you can imagine that the larger path length that goes into producing this ring might produce some other characteristic features, such as changes in the orientation of the electric field. And that's actually exactly what the Event Horizon Telescope is measuring in this image. They're measuring the direction that the electric field of the light is pointing. And so that might have information about this accumulated path length that you're referring to. So those are some ways that can manifest.
Thank you. My other question might be too technical, but and you might want to save it to the end. But I know several years ago, black hole firewalls were a big hot topic. Is there anything you can comment on about recent developments in that area?
So firewalls were a thought experiment that some theoretical physicists came up with as part of a long history of efforts to try to reconcile our understanding of Einstein's theory of relativity with our understanding of quantum mechanics. It turns out those two theories are in tension with each other. It's been very hard to come up with a self-consistent theory that in certain regimes looks like Einstein's theory of relativity and in other regimes looks like quantum mechanics. And firewalls were a thought experiment that suggested that something really weird might happen around the event horizon of a black hole when you tried to come up with a consistent quantum mechanical theory of black holes. I think there actually have been some remarkable developments in that, which is that this is all related to something that's called the black hole information paradox, which is that because nothing can get out of a black hole, you can't figure out what a black hole was formed from. So I can't tell you by observing a black hole, according to Einstein, whether the black hole was made up of the collected works of Jane Austen or whether it was made up of a bunch of shoes, right? Because that information is lost behind the event horizon. And you can formalize this into quantitative notions of loss of information in ways that are very problematic in quantum mechanics. And that problem actually looks like it has been solved in the last couple of years. There's two groups that have shown that, I would say it looks much more convincing than it ever has before, that black holes actually can get rid of some information in the form of what's called Hawking radiation. And in doing that, that actually solves this firewall paradox. So I think that actually might well have been resolved. So that's actually been a very exciting development on sort of the other side of why everybody is so interested in black holes, which is sort of the conceptual side of what they teach us about fundamental physics. So great question.
Thank you very much.
All right. Eliot, I see somebody named Tucker Hyatt ask this question. Were those mock images, images you referred to as mock, produced before the genuine EHT image was captured?
They were produced before the EHT image was. And actually, the first prediction of this was not work done by my group, but there was a paper in 2000 that made the first predictions that actually look very much like the observation. So,
wow.
Ours was done in 2012, 13, 14. So.
Very cool. Jim Stauffer has a question. Jim, please unmute yourself and fire.
Hi, this is really great. And for the interferometry, you put these on disks and then take them to a central computer. How do you align everything temporally? What technique do you use?
Right, so that's actually one of the hardest things about this technique. So for it to work, to trick the light, so to speak, you need to know all the information about the light as it hits the telescope. And that means you need to know whether the electric field was pointing up, down. So you need to know exactly what time the light hit this telescope and exactly what time the light hit this telescope. So they actually have atomic clocks at each site that allow you to have an extraordinarily precise measurement of time and use that to register the images. And then the other thing I would say is that this observational technique works in the radio where the distance between these are a millimeter. That's what it is for the Event Horizon Telescope. This is slightly schematic, but you can think of this as electric field is strong, electric field is weak, electric field is strong, electric field is weak. That pattern repeats itself every millimeter for the observations that the Event Horizon Telescope took. But it has not been possible to do this kind of measurement with light, for instance, that our eye can see. And the reason for that is that wavelength is much shorter. And so first of all, there's a lot more information you would need to record because the pattern repeats itself much more quickly. And second of all, you would need to have an absolute measurement of time better than what we can currently do in order to record exactly when the first peak or first trough hit the telescope. And so the need to be able to register the information at the telescope actually restricts what wavelengths you can do this kind of measurement at.
Well, that's pretty impressive that the resolution of the clock can be that fine.
Yeah.
There's such a short interval between waves.
That's right. This is, so 230 gigahertz. So that means the period exactly is less than a millionth of a second. Yeah, great question.
Raul, please, another question.
Yeah, sure. It's Rajal. I know.
Rajal.
It's very. There are lots of names, Rahul and all that. So I was just curious, and maybe this is common knowledge, but if the black hole has collapsed because of gravity, does it just continue indefinitely? Like, does it never die? Is there no way for it to die?
So in Einstein's theory, there is no way for it to die. Black holes are sort of the ultimate end state where gravity wins and that's the end of the game. But in quantum mechanics, we think that black holes can actually very, very slowly die. They actually very slowly emit a very weak form of radiation that's called Hawking radiation. And in principle, in the far, 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 far distant future of the history of the universe, all the black holes that we know of might have disappeared through this process of Hawking radiation. And that's related to the earlier question about firewalls that I was talking about.
Niti has a question. Please, Niti, unmute yourself.
Hi, yeah. So this is in context to your Hawking radiation that you just mentioned. I was just curious, that's something, to my knowledge, it's not something that's proved, right? It's a theoretical concept and there's no like proof or any kind of an evidence confirming it, right? Because I do understand if there is an Hawking radiation, then there's a way that the black hole emits some kind of an energy and light, and in contrast to black hole not emitting anything. So I think Hawking radiation is a way of the black hole emitting a radiation. But to what I know, I think it's something that's still very much in theory, but not proved.
That's exactly right. So all of the light that we see from black holes in nature is produced by gas around the black hole. The amount of light associated with Hawking radiation is absolutely tiny and completely unobservable compared to the light we're seeing from the gas. So this is, at this point, a theoretical prediction that you're correct, does not have any experimental support. It doesn't have any experimental refutation either. It's just been not possible to test. My guess is it will not be, I don't think it will be tested by actually directly observing Hawking radiation, because that is so hopelessly faint. I think the test will be more indirect, namely that the theory that gives rise to Hawking radiation is a quantum mechanical theory of gravity and a quantum mechanical theory of black holes. I think that theory will make other predictions that are testable and that will provide support for sort of the theoretical framework underlying Hawking radiation. But I have to say, it seems extremely difficult to directly, unless we can create black holes in the lab in some distant future, I think using astronomical observations to see Hawking radiation is going to be incredibly difficult. Great question.
Thank you so much.
Eliot, please make those black holes in New Jersey rather than California. Yes. Thank you, everyone.